Okay, and so in this example, let's look at the steel rod shown. It has a diameter of 10 millimeters. It's fixed at wall A, and before we load it, there's a gap there at B, and that gap's 0.2 millimeters. And so what's going to happen is we're going to apply a load of 20 kilonewtons on this, and we're going to assume that it's going to grow enough to touch the wall. And so that when it touches the wall, then we're going to have a statically indeterminate problem, because we'll have two reaction forces and we will have the load. So how do we go about doing this? Well, this is our perfect classical statically indeterminate problem. So let us draw our free body diagram, assuming that it has gone all the way to B prime and touched. And so what it'll look like once we do that is I will have a force of 20 kilonewtons here. And since it's pulling away from A, I'm assuming that my reaction force at A will be moving in that direction. Since I'll be pushing it into B, I'm going to assume that my force at B is going to be pushing back in that case. So now we draw our static equation. So sum of the forces in the x direction are going to be 0. So what is that going to mean? That's going to be 20 kilonewtons minus FA minus FB has to be equal to 0. Statically indeterminate. Can't solve this via statics. Now we need a kinematic compatibility equation. So we need our second equation. We'll just call that equation 1. Well, our second equation is our compatibility equation. I know the deflection between A and B can only be 0.2 millimeters, because that's all the gap that's there. Once I hit that wall, I can't expand anymore. And so we're going to need this in meters anyway, so we'll convert this over 0.0002 meters. And so that'll be our second equation. So that'll be the two equations that we'll use. Okay. So if I draw my free body diagram of my internals, so I'm going to make the cut right before I apply that load P, and then on the other side I'll look at it right after that load P. So I will have an internal load of FA pulling in tension, and then I will have an internal load in the second part, FB compressing. And so now what do? I can put my two equations together. Let's start out with my compatibility equation. So I know from A to B, the most deflection that I can have is 0.2 meters. And so how do I calculate that out? Remember, deflection is equal to the sum of all the PL over AE. And so that's going to be the force in A over the length which it is applied. So that internal force is AC divided by the area times the modulus of elasticity. Now, in that second one, we've got compressive. Since it's compressive, it's negative FB L between B and C over area modulus of elasticity. Now, see, this one is kind of nice because they all use the same area and modulus of elasticity. So I'm just going to multiply that through to just make the math a little bit easier. So 0.0002 meters times the area. So pi over 4 d squared, and that is a 10 millimeter bar, correct? So 0.1 meters squared, because we want to convert everything over into meters, times the modulus of elasticity, 200 times 10 to the 9th newtons per meter squared. And this is why I converted everything into meters, because I want everything to cancel out appropriately. So there's all my left-hand side of the equation. That's going to equal the right-hand side. Well, the right-hand side is going to be the force in A times the length of A. So LAC is that length over which that internal force acts, which is going to be 0.4 meters. I'm going to subtract from that FB over the length over which that FB force is there, which is 0.8 meters. So now at this point, we've got some stuff that we can multiply together. And if we do that, what we'll have is 3141.59 newtons time meter on the left-hand side. And that's going to just be equal to 0.4 meter FA minus 0.8 meter FB. So now I have my equation simplified. And so we go back to what's our other equation, and that is going to be that 20,000 times 10 to the 3 newtons is going to be equal to FA plus FB. Okay, and so now we have those two there. If I take this guy here, plug it into the first one, it doesn't matter how you do it. Once again, you could sit there and you can either go 20,000 e to the 3 newtons minus FA is equal to FB, or you can sit there and go 20,000 times 10 to the 3 minus FB is equal to FA, and then plug that into this equation. Doesn't matter which one you use, you'll get the same answer. So we'll have FA, and FA is calculated out to be 16 kilonewtons. FB will calculate out to be 4.05 kilonewtons. Much higher reaction force at A than there is at B. So, now the question becomes, because we had a gap there, how are we sure that we're filling the gap? If when we would have calculated this out, because remember, we got this negative in here for B because it's in compression, so it knows it's in compression. Just like, remember from statics mechanics, I have a positive answer here. What does that mean? It means I picked the right direction for my arrows. If this would have come out to a negative quantity, well, the problem would have been statically determinate, because if the only way that you'd get a negative reaction force there is if it's not touching and it had to be pushed out to grab it. By the nature of this being positive, it tells us, yeah, we made the right assumption, it's going to grow to the end of the wall. If it would have been end up negative, then what you would have said is it never touches the wall, and you would say that, okay, the force at A has to be 20 kilonewtons, because at that point it's statically determinate.